Good evening, Professor.
Good evening, everyone. It gives me immense pleasure to introduce the esteemed speaker of the session, Dr. Srinath MK. Dr. Srinath is currently working as an associate professor in the Department of Mechanical Engineering, New Horizon College of Engineering, and is with the institute from the past 2011. He has got around 12, total 10 plus years of experience in teaching PG and UG students and has guided about 40 students projects. His area of research are composites, nanomaterials, metal coatings, and additive manufacturing. Professor has published 20 research articles in reputed journals such as Springer, Elsewhere, Taylor and Francis, Materials Today, etc. And he was consecutively awarded as the best paper publication in marine engineering divisions. He has received a grant of rupees 40 lakh from VGST and has set up the Biomechanical Center of Excellence for Research in the Department of Mechanical Engineering. I welcome Dr. Srinath MK on behalf of Mechanical Department, New Horizon College of Engineering, to deliver the talk on additive manufacturing. Over to you, Professor.
Thank you, Professor Rakesh. Thank you for that wonderful introduction. Sir, I hope I'm audible.
Yes, you're audible, Professor.
Yes. Okay, sir. Then I shall start with the presentation. So, good evening, participants. I can see that there are a mixed bag of participants over here. I believe most of them are from the academic field. So today, I've been asked to give a presentation on additive manufacturing. So as you people already know, this is a Atal Faculty Development Program sponsored by AICT and organized by New Horizon College of Engineering. And I'm also part of New Horizon College of Engineering. I am from the Center of Excellence for Biomechanical Engineering Sciences from the Mechanical Engineering Department. Right. So today's session is on additive manufacturing. I'm sure most of you have already have a general idea as to what additive manufacturing is. There may be other experts also, but I would go under the assumption that I will take it as an assumption that I'm introducing this topic to you as a new topic. So let us proceed now, right? Yeah. So this is going to be the set of contents that I'll be sharing for today. So starting with the definitions, what is additive versus subtractive manufacturing, an introduction to additive manufacturing, and what exactly is additive manufacturing, then the evolution of additive manufacturing, what are the advantages, limitations. We have two case studies, case study 1 and case study 2. Then we will go ahead with the difference or the comparison, as I would like to say, between 3D printing and CNC machining. After which we will proceed with the stages of additive manufacturing, classification. Then in precise, I would like to talk about fused deposition modeling, because I feel that fused deposition modeling is very much into the research topics nowadays. Then I will have a small demo on the modeling and 3D printing process that I will show from my lab itself. Right now, I am currently in my lab in my center of excellence. After which, then we'll go to the post-processing of AM parts, that is additive manufactured parts, applications, and not many people may know, but there are a few simple problems that can also be integrated to additive manufacturing that I'm sure that we can look into it in a very easy manner. Okay. Yes. So the very first topic, definition. What is the definition of additive manufacturing? So this additive manufacturing as a point, it defines as refers to a process by which digital 3D design data is used to build up a component in layers by deposition of material. Yeah, so this additive manufacturing definition which has been provided over here, I think holds good for all the additive manufacturing techniques or the different types of processes that we will be coming across. Okay, so what basically we always have is a 3D design data, a 3D model, a digital model, which can be modeled using various techniques or various methods, after which we will be having one minute. Yeah. After which the process is to build this particular component. How do we go about building this component? As the definition states, it is a deposition of the materials in a layer by layer manner. in a layer by layer manner, the material is deposited, right? So additive manufacturing versus subtractive manufacturing. I think the difference between the additive manufacturing and subtractive manufacturing is quite visibly clear over here in this particular image. Let us take up the topic of the subtractive manufacturing first. Now, when we talk about the subtractive manufacturing, the word subtractive itself defines or states that the material is removed in a step-by-step manner, okay, so that we get our final object. So if you see the first image, we have a material in a cubic form, okay. Then we have subtractive manufacturing or the various processes that it might involve, basically drilling, turning, milling, or any other finishing operations. Then we have the 3D object. And when we talk about the additive manufacturing, the material need not be in a cubic form or in a solid form at all. It can be in any of the form. It can be a solid, it can be liquid, or it can be powder. Obviously, I'm sure some of you would have thought a solid, liquid, and gaseous. So please take it out. So it is solid, liquid, and powder form. So when this material, it can be in any of these forms, and the material is added in a layer by layer or a step by step manner, and eventually the 3D object is finally obtained. Now, using subtractive manufacturing or using additive manufacturing, the 3D object obtained is the same. The 3D object obtained is the same. However, when we observe the waste, there's a vast difference. There's a vast difference. The waste obtained in a subtractive manufacturing is very high, whereas the waste obtained in an additive manufacturing is very low. So this is one of the bigger advantages. Of course, there are other advantages to this particular process, but the basic understanding of subtractive manufacturing is the material or the final object is obtained from the main object by removing the material, whereas in additive manufacturing, the final object is obtained by adding the material in a layer by layer manner, right? Just a second. I think I went. So as I was just telling you, what additive manufacturing? Yeah, additive manufacturing is a technology which can manufacture any component. What does this manufacture any component means? Literally, it means any component only. There isn't no holding back in additive manufacturing. Additive manufacturing can literally manufacture any component. I believe some of you may have read an article of late. There are cars, bikes, or I think Elon Musk has also come up with a rocket which he says that the entire rocket is additive manufactured. So including the engine components, everything that is involved in it, it is additive manufactured. So as the first point mentions over here, additive manufacturing is a technology which can manufacture any component, literally any component. The next point mentioned over here is eliminates many constraints imposed by conventional manufacturing techniques. What could be this constraints imposed by conventional manufacturing techniques? Now, if we talk about any conventional manufacturing techniques, such as let's say turning or milling or drilling, what are the constraints involved in there? We have the speed, we have the rate at which the material is removed. Okay, we have the depth of cut. Okay, so such constraints need not be present in our additive manufacturing technique. And finally, obviously, the third point over here mentioned is leads to numerous market opportunities. The market opportunities for additive manufacturing is very vast. Okay, right? Um, as mentioned over here, additive manufacturing is an appropriate name to describe the technologies that build 3D objects by adding layer upon layer of material, whether the material is plastic, metal, concrete, or one-day human tissue. I think that one day is completely inappropriate. I think people have already started additive manufacturing of tissues also over here. There is concrete is also mentioned over here because we already know that there's a 3D printed houses coming up already. So what happens is the concrete is poured in layer by layer manner, and the house is built. So that is also happening right now. So plastic, metal is where we have a laser powder bed fusion technique for metal 3D printing. And obviously, yes, human tissue is also happening over here. That I think lot of research is happening, a lot of work has already happened also in case of biomaterials or human tissues. But still, it's still a long way off, but it has very much started already. Now, next part over here, I'd like to discuss, continuing with what exactly is additive manufacturing is. It is common to AM technologies is the use of computer 3D modeling software. So CAD, machine, equipment, and layering material. So use of computer is a must in case of additive manufacturing techniques, because we need to model the particular software, particular component, okay, using the necessary software. There are different modeling softwares that can be made use of. Okay, then after which we need to slice the material. I think I'm going a little ahead of me, but yes, computers are very much needed for us. They are very much part of this process. Okay, the software is involved, then the Cura software that is involved, that I will be discussed in the forthcoming in the steps. Then next point mentioned over here is once a CAD sketch is produced, the AM component reads the data from the CAD file, lays down or adds successive layers of liquid powder, sheet metal, or others in a layer by layer manner. And finally, the term AM, additive manufacturing, encompasses many technologies, including subsets like 3D printing, rapid prototyping, digital manufacturing, direct digital manufacturing, sorry, and layered manufacturing, right? So what is additive manufacturing? So as the name suggests, it uses an additive process. So I think it's only logical that we make use of the word additive manufacturing. So I believe the other conventional processes, they were not called as subtractive manufacturing until the technology of additive manufacturing came about. So until additive manufacturing came about, the other technology, other manufacturing techniques were just called as manufacturing techniques. But when the technology of additive manufacturing came about, then obviously it was only logical to call them as subtractive manufacturing. Now, this process obviously involves the joining of materials to make objects from 3D model data, usually in layer by layer manner. So commonly known as 3D printing, and able to manufacture components with virtually no geometric limitations or tool. No geometric limitations. There is no limitations to the size or intricacies or complexities of the model. And tools, we only need a nozzle which can extrude the material and add the material in a layer by layer manner. We do not have any other tools, or majorly we do not have any other tools, such as any cutting tools are not being used over here in 3D printing or additive manufacturing. Now, this particular point, additive and subtractive manufacturing of a cup. This is another small minor case which I'd like to discuss over here. We have a simple cup in front of us. Now imagine, how do we go about manufacturing this cup in subtractive manufacturing, and how do we go about manufacturing this cup in a additive manufacturing process? Now, if we talk about subtractive manufacturing first, how will I go about this? So what I will do is, so people see this cup. I think, is my mouse visible over there? I hope my mouse is visible. So this subtractive manufacturing, I will be taking a cube of this particular size. Okay, I'll be taking a cube of this particular size, and slowly what I would have to do is I need to remove the material inwards, and I would also have to remove the material outwards. And I also have to ensure that this cup handle doesn't break during the process. This cup handle doesn't break during the process. And even more so, when I'm trying to, let's say, when I'm trying to remove the material from the top, it would be easy. But imagine what I would have to do when I have to remove the material both in the X direction and in the Y direction, as well as in the Z direction. It would be very, very difficult to remove. But however, when we look at the subtractive manufacturing, when we look at the additive manufacturing of the cup, all we have to do is we need to slice it into various layers, and then we need to simply add the material in a layer by layer manner, and we would be getting the cup. So imagine what would happen for a simple cup itself. We are saving so much of material. Okay. However, if we are to do more intricate objects, complex objects, or components, it would be much more feasible, right? Now, this is a small table that I've been able to obtain online. The evolution of additive manufacturing. So as you can see over here, the entire process was initiated in the year 1988, basically as a rapid prototyping. Then in the year 94, it came about to rapid casting, then which proceeded to rapid tooling. From 2001 onwards, additive manufacturing started coming about for from the applications point of view. So for automotive parts, then 2004 for aerospace in terms of polymers. Then 2005, it slowly started moving outside engineering, that is in the medical field. Medical field, basically it was used as a guide or a jig for the doctors to perform their surgeries. Okay. Then in 2009, where the first medical implant was used in terms of dental implants. Okay. Dental implants were used. It was started, it wasn't fully established, but however, it was started. Then 2011 onwards, metal 3D printing was initiated. Of course, it was incorporated into the aerospace aerospace applications. One second. Yeah. Then architecture, then 2013 onwards, it came to biomedical implants. Then we have in situ biomanufacturing based on specific requirements and conditions based on the each case to case from patient to patient. As I mentioned before, 2013 onwards, organs, that is human tissues, have started um, have been applications have started in 3D printing or additive manufacturing. Here, what happens in tissues, 3D printing of tissues, human tissues or live tissues, is cells are added in a layer by layer manner or in a step by step manner. Okay, in an organic material, so that live cells are being added and they are allowed to grow. They are allowed to grow. Once they are grown, these tissues are incorporated into the humans wherever it is needed. Right now, only tissues are being 3D printed, I mean, additive manufactured. Okay, so for basically muscles, any skin damages, for that reason, the additive manufactured tissues are being used. However, organs are not, or to the best of my knowledge, organs are not yet incorporated. I think that is that is most likely to happen in the next decade or so. But I'm sure it will be there. It is not far off, right? So as I was talking to you, I think so far I was talking a lot about advantages in general. So to customize it or to make it in a short form, I've just made over here 8 different advantages to this particular uh, additive manufacturing. So the first and foremost, obviously, is the freedom to design and innovate without penalties. So there is no limitations to the design. There is no limitations to the intricacies of your model. There is no limitations to the complexities of your model. Any shape, any design can most definitely be manufactured using additive manufacturing technique. Next, rapid iteration through design permutations. So if at all any changes that can be done, it's most definitely possible. Then we have excellent mass customization. So mass customization meaning for specific set of people, such particular components can be designed or manufactured for that set of customers. Then elimination of tooling. Obviously, elimination of tooling. There is no cutting tools happening over here. Then green manufacturing. Why I added this green manufacturing? Because there is no waste. There is absolutely no waste happening over here. So pretty much, yes, this is a green manufacturing technique as long as there is no waste happening. There or not no waste, minimal waste. And as the next one very precisely states, minimal material is wasted. I think this point was discussed in the very second or third slide. Whereas in additive manufacturing, very little material is wasted, and in the subtractive manufacturing, the entire lot of material is wasted. Then the seventh point, uh, energy efficient. Energy efficient, obviously, because everything is with respect to energy. 3D printing, the the power is not wasted. Then finally, we have enables customized manufacturing. Enables customized manufacturing, meaning this 3D printing can be done from person to person. It need not be that it has to be only for a mass group of people. It can be changed as per a single person's requirement, right? So obviously, when there are advantages, we also have disadvantages when it comes to additive manufacturing techniques. Okay, there is nothing, there is no process in this entire engineering wherein which has only advantages and absolutely no limitations. So obviously, the first one is unexpected pre and post requirements, processing requirements uh, will be needed. So there are cases where the filaments or the materials will have to be pre-processed. So let's assume, for an example, I have to build a composite 3D printed component, a composite material of a PL of a polymer reinforced with a ceramic. So directly I cannot print it with a PL with the polymer material and then add the reinforcement. What I will have to do is I will have to produce a filament which consists of the polymer and which also is got reinforced with the whatever ceramic material or whatever additional material that we have. So this becomes a pre-processing requirement, whereas the post-processing requirement depends on how the application or where the application is. So application wise, it may not have a very good surface finish. For example, it may not have a very good surface finish. In that case, what we need to do is we have to ensure that the component has got good surface finish. So a post-processing requirement is a must. We'll have to produce or we'll have to provide a material with good surface finish. So coming to the second point, high process cost. Yes, this is a very high process cost. There is no doubt about it. There is no doubt about it because we need to extrude the material. We need to 3D print. Okay, and most of the process itself is a very high cost. Lack of standard industrial standards. Now, lack of industrial standard. Why I'm speaking about lack of industrial standards over here is because there are no set of standards as established as of now for additive manufacturing. So, if I were to take as a mechanical engineering, I would like to take, for example, what are the standards for a tensile test of a material. So in that case, there are ASTM standards, there are ISO standards, there are different standards set already, but there are no preset standards for additive manufacturing. Additive manufacturing. So a lack of industrial standards is still lacking over here. Then the fourth limitation is low speed. In additive manufacturing, it is not a fast process. It is not at all a fast process. It is most definitely a slow process. Slow process is because the material is being added in a layer by layer fashion, and the material needs to fuse with the pre-existing or the layer which has been laid out before. Okay, so the process is very slow, and it can take a lot of duration. So unsuitable for mass productions. The next point over here, unsuited for mass productions. Why we are talking about unsuitable for mass productions is because in mass production, what happens? We're talking about components of 100, 200,000. But since there is this process itself is a high cost process, there is lack of industrial standards and there is very low speed. Mass production is not possible because to produce, let's say, 100 components, it would take let's say, by additive manufacturing, a component takes about 4 hours. Okay, so if I were to if I were to produce 100 components of that, that will be multiplied by 100 into 4 hours. So that will not be possible. If not, I need to have 100 machines printing the same component. So that would again go ahead with the high process cost. So there are a lot of lacuna in that terms. Then finally, the next point, 6 point over here is limited number of materials. So limited number of materials, obviously what I'm trying to say here is materials such as polymers, the very first ones which have been started off. Then this one, metals are being used. So after metals, now biometals are being used. So obviously what I'm trying to say is materials such as, let's say, for example, fabrics are not being 3D printed as of now. So that is still a long way off that is happening. And finally, high equipment costs. Equipment costs, 3D printer equipments vary. The cost of equipments can vary, starting from about 10,000 to 20,000 rupees, and it can go up to 15, 20, even 30 lakhs. That is, I'm talking about with respect to polymer additive manufacturing material equipment. When I talk about metal, that is laser powder bed fusion, the cost of that particular additive manufacturing equipment can go in up to crores. So obviously the equipment is very high. So if I'm going to, if let's say I want to 3D print aluminum alloy, I would rather have it done by through subtractive manufacturing or through conventional manufacturing techniques. I will not be going it with laser powder bed fusion. There is no logic in doing a laser powder bed fusion of an aluminum alloy, right? So, but of course, there are reasons why I would say that I will go ahead with the aluminum alloy 3D printed. Could be to reduce further density, because it will not be having 100% infill density. The infill density can be reduced to maybe 50, 40, 30, 20, how much ever that we want, right? Or pattern, what kind of pattern, that infill pattern that we need. So such things can most definitely vary in additive manufacturing. Why we choose additive manufacturing techniques? It can definitely vary from requirement to requirement, right? But however, uh, the additive manufacturing equipment is very, very costly. Yeah, as I was telling you over here, um, this is a small case study that I have. What is the benefit, like benefit of additive manufacturing, that is weight reduction. So what we have here, the very first one, traditional design. This is a buckle which was designed for aircraft seat belts. This buckle was designed for aircraft seat belts. Obviously, this is manufactured through the conventional techniques. Okay, so through this technique, what we do is we have a conventional steel buckle, which, as mentioned over here, it weighs about 155 grams. Okay, now the other one which we can see over here, an optimized design. Now, this optimized design, what it does is it removes the material as in where the places it is not required, without compromising on the strength of the buckle. So, and the material has been changed from steel to titanium to make sure that, excuse me. So obviously, this one strength has not been compromised over here, but the strength weight has been reduced to, excuse me. The strength has not been compromised, but then the weight has been reduced from 155 grams to 75 grams. So if anyone may think, what is the point of changing it from steel to titanium, and what is the point of reducing it from 155 grams to 70 grams? So let us assume this very slide, the case study has been provided. Now, for a typical Airbus, an aircraft which has got about 380 seats, including all the seats, totally all the economy and the first class, second class, whatever it may be. We have about 853 seats put together, which all these seats, if I have about 70 grams of this particular buckle, it reduces the weight by 72.5 grams, 72.5 kgs. So 72.5 kgs difference is equal to that of a average human weight. Now, over the aeroplane's lifetime, so if I were to make use of this particular reduce the weight, so 3.3 million liters of fuel approximately is reduced, which is equivalent to about 2 million euros could be saved, and about 45 liters per kg and could also be saved over the entire airplane's lifetime. So that we see that using this optimized design through additive manufacturing, what we have obtained is we have been able to reduce the the fuel consumption, and we have also been able to save. Of course, there is a catch in this also. mass production. 853 obviously buckles have to be mass produced, means there is another time consuming process to manufacturing this. So both have pros and cons, right? The second case study which I would like to discuss over here. The first one is dental cross bridges. Now, dental cross bridges are used for obviously for dental applications. Okay, so this is a combination of polymer materials which is being used in dental implants. Okay, right now it is still under a lot of research has happened in this, but still a lot of research is yet to happen. Okay, I'm also doing a study on this dental implants using magnesium alloys and using biocompatible reinforcement to increase the strength for teeth replacement. So there's a lot of research, vast. The field is very, very vast. Okay, so this could definitely help the, the patients. Of course, this is based on person to person. Okay, individually it can be customized. Obviously, I'm sure all of you know that the dental structure of every human being is not the same. So from person to person, the dental structures can be verified, and it can be improvised based on the person's dental structure. Then the other one which we have over here is the bone implants, which we have. The bone implants, it can be used as the name mentions, as a bone implant itself. So if a human being has suffered a tragic injury, hopefully in a good manner, not resulting in death, but then the bone is shattered to the degree that the person doesn't survive. So obviously, let's say over here the person's skull has been fractured, or he had to undergo a surgery wherein the skull had to be fractured and cannot be replaced. So in that case, what is done is the structure, the skull is that particular portion is manufactured using 3D printing. It is customized based on the person's requirement or the patient's requirement, and it is implanted obviously with the help of doctors. Okay, it need not be that it is only at the skull. It can be at the any part of the body, basically the bone, the arm, leg, ribs, anywhere. Okay, so it is basically, it can be customized from person to person, from individual to individual, right? So as you can see over here, 3D printing or additive manufacturing is very advantageous when it comes to medical fields, right? So obviously, yes, so far we have seen various differences between 3D printing and CNC machining. So I think I'll just run through this. So 3D printing is an additive manufacturing and CNC machining is subtractive. Okay, and starts with a block of material. CNC machine starts the block of material, whereas to cut away or to remove the material in a step-by-step manner, whereas additive manufacturing, the material is added. So 3D printing and CNC are compatible with a wide variety of materials, obviously plastic, metals, even wood is also one of the materials. Obviously, yes, the most commonly used plastics include ABS, nylon, polycarbonate, PLA, PP, PP, PMA, PEK. So this polymer materials are common even for conventional manufacturing techniques. That is including your CNC machining also. So this is the same. Now, this is just a comparative figure of PLA, ABS, and a nylon material. A structure which any type of structures can be designed. So imagine if we were supposed to design this particular structure using conventional manufacturing techniques, how would it be possible? Please think it over, right? Now, let us get a little bit into this stages in additive manufacturing technique. So I would like to give a small explanation over here. What are the different stages in this additive manufacturing technique? So obviously the first one is the CAD model. Okay, then converting it to the STL file, then transferring the file to the machine setup, build, remove, post process, and applications, right? So this example that you can see over here, we have the first one is the CAD model, that is of a cup. Then it is converted to the STL. Then the file is transferred to the machine. Okay, the machine is set up. Then the material is added in layer by layer manner. Okay. So once we get the material, it is removed and it's post process to finish, for example, to finish to provide a better surface roughness. Okay. And finally, application. Obviously, the person over here is drinking a cup of coffee or an espresso. Um, so step one, CAD model. So all the additive manufactured parts must start with a 3D model. So this 3D modeling can be done using different modeling softwares. There such as Fusion is available, CATIA is available, Solid Edge is available. There are different models. Okay, so that is where you are actually modeling from the scratch. There is also a possibility of reverse engineering. Okay, such as laser scanning, wherein there is a laser scanner which scans the model and it eventually provides the model after it scans, right? Then converting it to the STL format. So converting it to the STL format in the necessary software that I will also be showing how the CAD model is converted to STL format and it is removed or it is sliced. Slice meaning the different layers are obtained. Then transferring the STL format to the 3D printing machine. Obviously, this can be done through data cable or through any other modes of transferring. You can pen drive is used, SD cards are used, right? Machine setup. We provide what is the initial setup for the machine, what are the material constraints, what material we are doing. Maybe we are using a plastic material such as a PLA or any composite material, whatever it may be. Then comes to layer thickness. All that will be provided in the machine setup. Built, as the name indicates, the material is built in a layer by layer manner. Okay. Yes, this does not require supervision. Okay. The material can be initiated, it can be started. The person need not stand there continuously to observe if the material is being built in a layer by layer manner. But however, this is a must and this is a requirement in conventional manufacturing techniques, right? But CNC machining, again, it would not be really required, right? Then obviously removal of the material after the component is built, we would have to remove the material and then we will have to provide the remove the from the bed. Then post processing. Post processing is, as I mentioned to you all, this is a requirement. This would be required from application to application or component to component. And finally, applications where we are going to use. That is where we'll be apply the component. Right. So before I go on to the classification, I would like to show you all a small demo. Please hold on. Yeah. Yeah. So what we can see over here, is a small what we can see over here is the Cura software which I've opened. Okay, so this Cura software makes use of or does the slicing for us. This is where we give our inputs to the 3D modeling process. uh, the the first step is a file wherein we can open the file. So I have just prepared a simple 3D model, a cube, in fact. Okay, so a 3D model of a cube. So once this is done, yeah. Now, obviously, this component, I don't want it so big. So I can, one second. Yeah. So we can reduce it to maybe, let's say, um, we can scale it down to a smaller component. So once this is done, so I've reduced this component. Now here we can see what is the strength that we'll give. So there are some components which will be required. The first one is obviously infill density. I can give 20%, 10%, 30, 40, how much ever we need. So I'll select, there are different types of infill patterns that can be selected in this. So different types of infill patterns are grid, lines, triangles. So cubic subdivision, octet, zigzag, cross, gyroid, different choices are available for us. So based on the strength requirement, we can select. There, this is a cubic. So what we see over here, the shell thickness. Shell thickness is for the side walls, it is mentioned as 1.2 mm. So what is the shell thickness? Is the outer layer of the entire cube, that is about 1.2 mm, whereas that is only on the outside. Whereas this one, what you see over here, the second one is for the upper layer and the lower layer. The upper layer and the lower layer, the thickness is about 0.8 mm. So I will, that has been select, that is automatically selected, and I will not go to change that. Okay. Then next one over here is support. Now, what exactly is the support that we generally see? In support, what we have, let's say, for example, I have a structure starting with a lower size and it growing up to a larger side at the top. So what happens is the side, the material has to be designed in such a way that certain supporting structure has to be there. So, but since this is a cube, we do not need support structures. So we will be removing that. And addition, so addition, we'll leave that addition as on, because I want to ensure that the cube is adhered to the bed. So this is the bed of the 3D printer. Now all of them have been selected. Now next I will go ahead to the slice. The slice, it says 56 minutes. Obviously, I'll not be able to go ahead with 56 minutes. Um, what I will do is I'll reduce it to, let's say, 1,000. Okay, and I will give the same infill density, 30% cubic, all that I'll keep it as the same. Then again, I'll give it, I'll ask it to slice. Yeah, now it is saying 19 minutes. So 19 minutes is about 20 minutes. So, and here it also shows the grams or the weight of the material, and the 0.9 meters, that is the length of the filament that we are going to use. So we will save this to the disk. Okay. So I can save it. Now, go to that. Remove that. Yes. Yeah. So I'll say to my removable disk over here. Yeah, it is saved, right? The file has been saved. So I'll just switch over to my mobile, which I've also logged in over here. I'll stop the screen sharing in this. Yeah, so what we have here is the 3D printer. Mute that. Okay. So I'll insert the this one. I've inserted the pen drive. So directly I'll go with the print from the pen drive. So the model is already here. The G code has been generated. As you can see, over here, the G code for the 3D model is being generated. I'll just select and confirm. The printing has been initiated. The temperature needs to rise a little bit. It will take just a short duration of time. So in the meanwhile, I'll just like to show around my lab. So this is one of the basic 3D printer that we have. These two, which I make use of for my research studies. Where's the PLA with CNT? So this particular PLA with CNT, I have been able to extrude in my particular lab using the extruder machine, which we have over here. We have a RP extruder as well. So any kind of polymer material can be added in over here, and it can be extruded out of this nozzle. Out of this nozzle, it can be extruded. So that particular 3D printed component can be, once a PLA material has been extruded, this can be 3D printed, right? Yeah, I think the machine has started. So first, what it does is it tends to check the surface level. So initially, what the 3D printer material does is it tends to create a bed of its sort, okay, so that to increase the surface adherence. So we'll leave it at that. So here also we can see different components that we can 3D print. So based some engineering models that we do for our students also have been 3D printed over here. Okay, a basic gear set, a sun and planetary arrangement. What we have here is a meter box reading. Okay, so such complex intricate models can be 3D printed. Okay, yes, as I was telling to you just a short while back, this what we see over here is a 3D printed PLA material with carbon nanotubes. So this has been printed as mentioned over here with the nomenclature. This is a 2% CNT along with 30% infill density. 30% infill density. 3 is the number of layers, and H happens to be the hexagonal pattern or the infill pattern that we have provided. Okay. So different materials have been different components. We can use gyroid, we can use cubic. So different percentage of CNTs can be was implemented. This research is still under process. There's still a long way off. So I just kept the component here to show you all. So yes, the material is getting printed. So when in about 19 minutes, right? So 8% of the work has already been done. So in about 19 to 20, in about 20 minutes, we'll see the entire cubic model, right? So this is another 3D printer that we also have. This 3D printer has been used for little higher end research works. So these two are the basic 3D printers that we have. This over here, we have the RP extruder. The RP extruder is being used, as I told you, to extrude any kind of material. Yes, over here, what we see over here is the pellets of a PLA with CNT. Of course, this is the process is expedited in a 2 or 3 manner, wherein once it's extruded, the extrusion the filament is cut again, and then it is added again inside the hopper. Again, it is extruded. The process is continued at least about 3 to 4 times, because mainly because we need to also have um, uniform distribution of the material. Then this is the biological incubator. I think this is a little off from our topic, but then we do have a biological incubator. And we have a very high-end 3D printer also. Uh, this is a Minga 400D 3D printer, which costed us more than a few lakhs. Um, this has got a printing temperature of about uh, 400 to 500 degrees Celsius. So any material with very high 3D printing temperature, such as, like, let's say peak polyethyl ether ketone, that is a very highly biocompatible material. This biocompatible material is still is also one of the topics of my research. So that that particular polymer material will be 3D printed using the 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 high-end 3D printer over there. So this is under process. I think we'll come back to that a little later. So let me get back to the presentation as of now, right? Just a minute. I'll continue the share. Yeah. So these are the different steps that I spoke about just a short while back, and I showed it to you also in the 3D printer. I've just, as of now, I have done only a very small model in the in the 3D printing machine which I have over here. I cannot show a larger component or a more complex structure, because, as I told you, this is a very time-consuming process. Some of the larger components which I showed over there took us almost about 4 to 5 hours, or even some of them took even 8 to 10 hours. So we had to I had to give you a really just a small brief over there, right? Now, what are the classification of additive manufacturing techniques? Now, there are different classifications. The first one, obviously, yes, the classification is based on the type of material that we are going to use. So the first one is the liquid-based material. In liquid-based material, we have the stereolithography, jetting systems, direct light processing techniques. In the solid-based, we have the selective laser sintering, where a laser of material is passed onto the material, and it is sintered. The metal is sintered, and it is hardened, and it is adheres to the previous layer. So in the layer by layer, it is added over there. Then 3D printing. Then we have the fused metal deposition, that is your laser powder bed fusion, the electron beam melting, selective laser melting. So different techniques are there. Then when it comes to powder based, we have the fused deposition modeling, what I showed you just now, and the sheet stacking technologies. Now, this fused deposition modeling, this can come under both solid based and powder based. So how we read it, that depends, right? So I would like to discuss a little bit on the fused deposition modeling, since that is my larger interest or my more specific interest. So as I just showed you over here, fused deposition modeling FDM is a filament based technology where a spool of the material, is added in a layer by layer manner on a platform, so that the final component is obtained. So this obviously it's a the spool of the material. It is a filament basically. So in this technique, thermoplastic materials can be done. That meaning the material which can be melted and which can go back to its hardened state. So typical materials are ABS, PLA. There are different, and of course, PLA is a very good biodegradable material. It's currently being used uh, as one of the inserts in for medical applications, right? Many new materials are there, but still, as I told you, there's a lot of research still being conducted. Then fused deposition materials applications. So prototypes are being produced. Then there are supporting structures and fixtures. Okay, the small series components, so small parts, small components, like even keychains are also being produced. So it depends as depends on the application, the requirements of the customer. Now, what exactly is the post processing of AM parts? Now, as I told you, many different things are being, there are many different techniques, the many different processes can be done, many different component shapes can be done using AM. But there is something called as the post-processing of additive manufacturing techniques also. This post-processing is very much required. It depends on the applications. It could be a simple painting also, okay, for aesthetic purpose. That is also a post-processing, right? So it is an essential stage of additive manufacturing. It is the last step where the part receives the finishing touches, such as, yes, smoothing and painting. So why is it important? Let's look at that. The post-processing improves the quality of the parts and ensures that they meet their design specific standards as per the customer's requirements. Then the finishing process can enhance the part surface characteristics, geometric accuracies, aesthetic, mechanical properties, and more. Some materials also cure to increase the strength even more further. So that is also a post-processing in additive manufacturing parts. So what are the different applications of AM? See, we talk about additive manufacturing as from the application points of view. So let us look at what are the different applications. In rapid prototyping, food. There are many food industries and labs which have already started using additive manufacturing for food items. For example, chocolates and candies are being already being done. Then apparel. Shoes is one apparel which is also 3D additive manufactured. Shoes is, as mentioned over here, Nike is using 3D printing to manufacture football shoes for players. So that is also being done. Apparel can include even shin guards. Okay, it can be used for any other sporting events. Football players need shin guards because obviously they need protection from the kicks that they receive from on the shin. So that is also 3D printed nowadays. So one of my colleagues is actually doing a research on increasing the strength in shin guards using 3D printing technologies, using uh, some softer materials. Then vehicles, parts of the vehicles, the dashboards, firearms, medical devices, bioprinting. Now, this bioprinting is a very unique application of this 3D printing. So, as I told you before, as of now, 3D printing is being used for various applications, but that is only with respect to polymers and metals and other materials. So, and with respect to aerospace, naval applications, or automotive applications, or any other type of applications. But then bioprinting, what exactly is the bioprinting? Bioprinting is where the component is 3D printed component meaning the tissue is being 3D printed. So what is happening is in bioprinting, the living cells are deposited on a gel medium. So as you can see in the second point over here, the living cells are deposited onto a gel medium to slowly build up into a three-dimensional structure. So as of now, to the best of my knowledge, tissues are being 3D printed and they are implanted into the human being after surgeries. But a lot of research is also being done on 3D printing of organs. So organs on a larger scale are also being 3D printed. I read an article somewhere, I'm not sure exactly where, a 3D printing of the gallbladder is also being done. So that is one of the it's already been achieved also, and it is a perfectly functioning 3D printed gallbladder. But I cannot really provide you the details because I myself just got to know about it very late. But then it is very much in research happening right now, right? Now, obviously, SpaceX. So the entire SpaceX delivered was zero gravity 3D printer to the ISS. So Mr. Elon Musk is doing wonderful job for himself, where he is going ahead with the SpaceX program. So so far we spoke about a few things about right? So I have about 7:10 right now. Gopal sir,
Yes,
Gopal sir, can you hear me?
yes, sir.
Sir, what time do I need to stop?
7:30, sir.
So, because you have a Google form also that you need to share, right?
Yes, sir. 7:25, 7:30, sir.
By okay, sir. Okay, sir. Fine. By 7:20, by another 5:10. Actually, sir, I'll be finishing another. I suppose another 5-10 minutes. I may finish. 10 minutes I may finish, so that you'll have ample time for your Google form also.
Okay, sir. Okay, sir.
Okay, sir. Okay, sir. Yeah. So we spoke about only the physical aspects over here. Of course, I like a lot of maths. So these are the few basic problems that we can come across in additive manufacturing techniques. The first problem or that we have over here is a filament is extruded at 200 degrees Celsius, is cooling at to ambient temperature at 25 degrees Celsius. The convective heat transfer coefficient is H, that is 50 watts per meter square Kelvin, and the surface area is 0.02 meter square. Calculate the heat loss. How can we go about this? So I think the basic formula can be most definitely be applied. So the basic formula applied over here. So what is the given data? The first one is the heat transfer coefficient H, so that 50 watts per meter square Kelvin. And the surface area is at 0.002 meter square. Next, we have the filament temperature, which is at 200 degrees Celsius, which when I add 273 to it, it becomes 473 Kelvin. And we have the ambient temperature, or the typical room temperature at 25 degrees Celsius. So when I add another 273, it becomes 298 Kelvin. So obviously the solution, the question is to determine what is the heat loss in this process. So the heat loss for this particular one would be Q is equal to HA into T filament minus T ambient. That is basically the difference in the temperature. So we have 50 into 0.002 into 473 minus 298. So that makes it 50. Eventually, we have a heat loss of about 17.5 watts. Right? Next, next question I'd like to share with you all. What is the bond strength of a deposited filament? Okay. So that bond strength equation is also provided over here. So sigma B is equal to sigma naught into 1 minus e to the power of minus kt. So sigma naught is provided as 10 megapascals. K is at 0.5 per second and T is at 5 seconds. So what is the bond strength? So the bond strength, so we have the given data. I'm sorry, we went to the next slide. So we have sigma naught at 10 megapascals. We have the constant K at 0.5, and we have the time also at 5. So the equation is already provided for us that sigma B is equal to sigma naught. So first we calculated what is the e to the power of minus kt, which has been obtained at 0.0821. So when we substitute this particular value, we get the bond strength at 9.179 megapascals. So we can also calculate numerically what would be the bond strength of any 3D printed component. Okay, provided we know the initial bond strength and the constants and the time taken, right? The third problem or the final problem which I would like to discuss over here, a 0.4 millimeter thick filament extrudes at 200 degrees Celsius into an ambient environment of 25 degrees Celsius. If the convective heat transfer coefficient is H is equal to 40 watts per meter square Kelvin, calculate the heat loss per unit length for a 1 meter long filament, assuming the filament circumference is C is equal to 3.14 mm. So we have the given data over here. So heat transfer coefficient at 40 watts per meter square Kelvin, and the filament temperature and the ambient temperature is again at 200 degrees Celsius and 25 degrees Celsius. So, and the filament length is at 1 meters. The circumference is at 3.14 millimeters. So the solution is, first we can calculate what is the surface area. So surface area can be calculated as C into L. So 0.00314 meters into 1 meter. So that makes it 0.00314 meter square Kelvin. And again, we can apply the same formula what we applied previously. Q is equal to H into A into change in temperature. So eventually giving us what is the heat loss, which is at 21.98 watts, right? So this is pretty much the numerical calculation. So I'll just get back to the to the 3D. Oh, I'm sorry, I was in mute. So what we have over here is the 3D printed component which I gave of about 20 minutes back. So this particular component took just 20 minutes for us to print. But imagine this small component itself took 20 minutes. What would happen to, let's say, a larger component like this, or this particular component? This component took me almost 8 hours to 10 hours. Some of the components over here took even 9 hours or 10 hours. Obviously, this is one of the bigger lacunas in 3D printing. It's a time-consuming process. So coming back to our 3D printed component, so what we see over here is a bed. What we see here is the bed. So this bed is made for all the 3D printed components. It is a basic structure which is formed first so that to ensure that the material is adhere to the bed of the 3D printer. So if I were to give a very small component, it may not tend to adhere because the bed also needs to heat. The bed is made warm. It is ensured that this addition is ensured to the bed and it doesn't move. Even a 1 millimeter displacement from the bed will spoil the entire component itself. So this addition is strengthened by this bed, which is also 3D printed. So later on, this bed can cut off, and then the final component can, right? This. So this 3D printed bed. So, and we also have movable parts are there for us. Okay, different components can be manufactured. 3D printing is a very vast field. Multiple works can be done, multiple progresses can be done. Just a minute. Yes. So yes, that was the last of my slides. So thank you all very much. Any questions that anyone would like to ask? I'm open to any questions. So let me also say that we are also open to any research that can be done from this particular lab. Oh, I think I have a question in the chat. Just a minute. What are the key challenges in scaling up additive manufacturing for mass production? Sir, as I told just a while back, biggest key challenge would be the time. So when this particular small component, Praveen, get me that. When this very small component has to be manufactured using 3D printing, I gave an infill density of just 30%. So using 30% infill density itself, this took me 20 minutes just to manufacture this particular component. The infill density, as you people saw online, I gave just 30%. In that itself, it took me 20 minutes. So imagine if I were supposed to manufacture 100 components of this. So I will have to make use of only one machine. If I were to make use of only one machine, this that 100 components into 20 minutes, it will take me a very long time, basically. Or I need to have another challenge, which I have is I need to have 100 machines, which needs to be done. The same thing, if I were to manufacture this using conventional techniques, this would be more feasible for me. Logically speaking, yes, it will be more feasible. But however, if my requirement is most definitely that I have to have just 100%, 30% infill density. If that requirement is there, then I most definitely will have to go for additive manufacturing. Okay. Thank you, sir. Thank you, Mr. Shankar, Professor Shankar. Thank you very much. Any other questions anyone else would like to ask?
Participants, you can ask any queries which are related to this additive manufacturing. Before asking question, just you can enable the video.
Or you can type the question here also, not an issue.
They can type the question in the chat box also. We will receive the entire questions and the sir will answer.
Okay, sir, Gopal sir, I think everyone seems to have at least, I think basically most of you have a basic working knowledge of this additive manufacturing. So I think that's a very good thing. I'm sure there is like to share that this field is very, very vast. I thought initially when I took up this topics on research, I thought what much can be done. But then as and how I started researching, let me tell you, there's still a long way off. It is almost never ending. Okay, so most definitely we can go ahead with different materials also can be manufactured. Composite materials. Then when it comes to laser powder bed fusion, as of now, basic materials are being used. But what would happen if we were to 3D print using composite metals, like ceramics and alloys. That also is another field of research that can be done. However, yes, as I told you before, this does require a lot of initial funding. So that equipment costs are very high in case of 3D printing. However, if obtained, if the chance is provided to the participants or anyone over here, I'm sure beautiful works can be done. Right. So thank you, sir. Thank you, Dr. Gopal.
Sir,
Thank you for inviting me for this presentation.
Thank you very much, sir. Srinath, sir.
sir, 1 minute.
Thank you, sir. Thank you, sir.
Yes, sir.
Anyone
very much,
can
sir.
give this, sir, Hemant sir, anyone can give this feedback about this session with enabling the video. It will be good. Participants, anyone can share your feedback just to enable the video.
Sir, can I?
Hello.
Sir, 1 minute, 1 minute. I am requesting the people, those are the participants. Yeah. Yes. Yes, sir. Sony, sir.
Piyush Kumar Soni, sir. Sir, I think you are on mute, sir.
Am I audible now, sir?
Yes, yes, yes. You're audible now, sir.
Thank you very much, Dr. Srinath MK, sir, because the session I was continuously listening.
Okay.
And we are also helping out our students and the startups who are working with us regarding this additive manufacturing.
Oh, brilliant.
So,
Okay.
the technology is being used because we have the printers and the students are working on it and their prototypes they're making. So we understand how much is it important, and for Industry 4.0, as we have highlighted all the aspects which are required for additive manufacturing, this rapid prototyping, multi-layer manufacturing, layer by layer manufacturing. So as we are reducing the scrap and we are utilizing the best material out of it, and as you have told about various filament products as well. So these materials definitely we can use, and we need to promote our students in the colleges, like how these machines, these 3D printers can help out in making the rapid prototype products.
Yes.
With least utilization of the power as well as the material, and we can come up with more finished products using
Correct.
these 3D printers. And for Industry 4.0, as we are concerned about the automation, so these machines, as they're using the IoT as well. So with the remote sensing facilities, and still a lot of research is going on in this area, as you have beautifully highlighted all the aspects, how we can go through the research part. And as I can understand, like some students were working on its development of a machine. So they are making their own 3D printer, and the companies who are available in Coimbatore and other places in India who are actually manufacturing the 3D printers, we have to compete with the Japanese companies and
Yes.
some other like Chinese companies as well.
Yes.
So more use of 3D printers is there in the system. We can bring more glory to the platform, and
Yes.
the results can be better. So
Correct,
thank
sir,
you,
correct.
Srinath sir, for explaining all the things. The contents was very nice, and
Thank you.
I was there throughout, and I really enjoyed your session.
Thank you, sir. Thank you very much. So as of now, my research topics are on 3D printing, and we do a lot of that. My research scholar is working on a biocompatible 3D printed implants. So that is one of the research topics that is also being conducted from this particular lab. So a lot of things, as that is just one particular topic that can be done. There is others also that can be done.
I
So
want to
I'm
add
sure
one more thing, sir, if you
if
please
you're
allow
able
me.
to,
That
yes,
my
sir.
recent patent last month I have published that that patent is basically on implants only, and the a complete denture I have made, and I have also used a 3D printer here. So
Okay.
the entire denture we produced, and on that denture I have added some silicon cellulose composite lining so that the damping strength can be improved.
Oh, okay.
So that is also one of the applications, and extensively now this dentist and the dental labs are using 3D printers, and they are making good products, and they are actually those dentures who are made with the 3D printers are more reliable and highly biodegradable, because the silicon cellulose and that acrylic we are using basically for those dentures. So these 3D printers are compatible with those materials for what we are making the products.
Good, sir. Good,
Yeah.
sir. Yes, yes. The topics on research topics on the additive manufacturing and 3D printing is vast. And as you mentioned, sir, thank you very much for including that point also.
Yeah.
3D printing is also, it can be, it is being automated, where a 3D printer is controlled remotely. Plus, the 3D printer may be in one city, whereas the controller can be in another city. So
Correct.
that kind of automation is also being done in 3D printers right now. So yes, sir,
Yes.
most definitely 3D printers and additive manufacturing can most definitely are being automated now. Very good research topics that can be done out of this.
Yeah.
Gopal, sir.
Thank you, sir. Thank you,
Yeah,
sir.
thank you very much.
Yeah.
Thank you, sir. Thank you very much.
Yes.
I'll end this. I will exit
Just
the
a minute,
meeting.
sir. Srinath, sir. Thank,
Yes, sir.
thank you
Yes,
very
sir.
much, sir, for the informative session.
Thank you, sir. Thank you, sir.
On behalf of New Horizon Management, Principal, Dean, Director, HOD, and faculties, I thank the session speaker, Dr. Srinath MK, sir, for taking his time on transferring the knowledge on the topic additive manufacturing. It's a great learning for all of us. Really, thank you very much, sir. I also thank ACT Atal for giving us opportunity for conducting this program. Thank you all the participants for joining this session. So right now I'm posting the feedback link and the quiz link in the group, as well as in the Zoom link also. So in the chat box, I request all of you to kindly fill this link that is related to attendance, as well as the quiz link, so which will be enabled up to 20 minutes. So thank you one and all.
Thank you, sir.
Okay, sir. Thank you very much, sir. Thank you very much. And thank you, dear participants, for being such a nice group of participants. I think I also enjoyed a lot in the presentation. It was very nice. Thank you all very much.
Thank you, sir. Participants, you can attend this quiz as well as you can give the feedback. So take a 10-minute break. The session will be joined 7:40. Start new video. Good evening, one and all. Now, I would like to invite Professor Sunil Prasant Kumar to introduce our session speaker, Dr. Nagendra Jairam. Over to you, sir.
Good evening, one and all. Nagendra sir, are you there in the meeting?
Yes, sir. Good evening, sir. I'm there.
Yes, sir. Thank you. Thanks for the confirmation. It's my pleasure to introduce Dr. Nagendra J, Associate Professor in the Department of AIML at Acharya Institute of Technology, Bangalore. Dr. Nagendra holds a BE degree in Mechanical Engineering, a Master's in Mechanical Engineering, and a Master's in AIML from IIITB in collaboration with Liverpool University, London. With strong background in PLM, additive manufacturing, finite element methods, is a recognized expert in these fields and has made significant contributions in advancing knowledge in these areas. One of the key factors of effective data analytics is domain knowledge, and Dr. Nagendra has extensively applied AML techniques to analyze mechanical data sets, bridging the gap between AML and mechanical engineering. Today, he will share his insights on the topic of 3D printers in modern industry, focusing on the transformative impact of 3D printing technology on manufacturing, design, and production process. We are excited to hear from Dr. Nagendra and look forward to an engaging and insightful session. Please join me in welcoming him. Thanks for accepting our invitation, sir. Over to you, sir.
Thank you, Sunil, sir. Thank you, Gopal, sir. And also the team of New Horizon in collaboration with Atal FTP, Atal Programming to have a successful event of this 5 days FTP program. So I was there in the session of Dr. Srinath. So wherein most of the topics related to additive manufacturing was directly dealt by him. So it became very challenging for me to continue from where he left. Because from his session, he gave the entire insight of what additive manufacturing is. And also very lucky enough to see the practical working of the additive manufacturing, that is through FDM printer also. Now, having said that, to continue from where Professor Srinath has left, so I'd like to engage the gathering with the implementation of AI in the same 3D printing. Okay, so this is my last minute change of what has provoked me after Srinath's presentation. So this is my last minute alteration in order to match with the flow from where he left. So can I share my screen, sir? Is it enabled?
Yes, sir, you can share.
Yeah, just a minute. Is the screen visible, sir?
Yes, sir.
All right. So this was my initial proposed topic of having 3D printing in modern industry. But now, as I told you, the last minute changes is now in AI in 3D printing. Okay. So my topic is on, this one. The content of my presentation these are my 4 contents, out of which the first two contents are completely swept away by Srinath sir. So now to have an introduction of what additive manufacturing is, as what Professor Srinath sir told. So it is a 3D printing technique wherein a material gets deposited layer by layer, and over which we now get to see the different models being printed with and without the supporting structures. Now, however, these materials are, it could be the polymers and also the composites, which is a composite like polymer having different combinations of matrices and also the metals with the different compositions. The way how we print it is we follow the same point-to-point method, or basically layer by layer driven, and also by using a computer-aided model, we would be able to generate the actual model by following the process of how Professor Srinath told, like creating a CAD model and then slicing it, and then slicing it through the Cura software and making the necessary preparations in the machine to have a proper validated printing by using the effective process parameters. And then the post processing is what has been done. Now, this is what we are now primarily looking into, like why additive manufacturing. Like additive manufacturing, it's a technique wherein we now build the material layer by layer, which uh, has a very minimum waste into it. And then the design complexity, yes, this is slight challenging because once when we get to see a different overhanging product, so that's where the system is now able to make a generative AI. I mean, through generative AI technique, the supporting structures are automatically built in order to make the model printable in any of the direction. That is one latest advancement. And then the speed. Right now, we are in a slightly slower speed as compared to the traditional machining. But still, there are many different parameters which are now getting added on to the software part of the 3D printer, which enables us for the faster printing, which includes the cooling rate and also the dual extruder nozzles. So with parallel printing, so there are a few upcoming technologies which are now getting evolved in the 3D printer also. So this happens to be one of the differences which we now get to see between additive and traditional manufacturing. Now, introduction to additive manufacturing. So we get to see few parameters. I mean, few key important techniques which play a vital role in today's market of additive manufacturing, starting with SLA, FDM, SLS, direct metal laser sinting, binder jettings, and electron beam melting. These, however, techniques use different materials into it. So the classification or the laser selection for each of the machines are completely dependent on the material that has now been processed into it. The lasers what we use for polymers are completely different from the lasers what we use for the composites, or basically the alloys, which could be the CO2 lasers or like helium cadmium lasers, and also different lasers which are now being used. So this is what the primary introduction of what additive manufacturing is. Now, the manufacturing technique, what we have here is, it starts with the design phase. That is where we get to see the CAD model getting generated, and then the file preparation, which gets converted into the standard tessellation language, that is .stl file. And then the printer takes care of the layer by layer printing after slicing, that is through Cura software. And then post-processing is the one wherein we look into the cleaning, curing, and the finishing of the products. So this is the overview of the additive manufacturing. Now, as I told you, like I'll just be taking you to a case study wherein our machine learning and AI has now been implemented into the FDM process parameters. Now, this is, I'll just be taking you through the Python notebook, which has a complete insight of what we have done here. Okay, so before I getting into that, I'll just show you the data set of the data what we have gathered for the present investigation. Now, this is a 3D printer that is fused deposition modeling data what we have. In the first column is the experiment number. Second column is the layer height, which is between 0.1 mm, 0.2 and 0.3, that is 0.1 to 0.3 mm, followed with infill density of 50, 60, and 70%. It goes on 50, 60, at which the extruder has now been moved over the bed while printing. Here we have taken the limit of 30, 40, 50 millimeters per second. And then the Young's modulus of the material. Now here we have tried out with the different materials. We have tried out with PLA, we have tried out with PLA, and then PC, polycarbonate, and then different materials with different Young's modulus. we get to see 4 different Young's modulus value here, wherein all the 4 represent different materials. Once when the products are printed, the bulk modulus of the material is now been tested for the serial number 1 combination, and then the ultimate bending stress is now been determined for the experiment number 1, that is the product printed through experiment number 1, and then also the compression modulus followed with compression strength. Now, in the present investigation, what we are now trying to do here is we are trying to predict this ultimate bending strength. This becomes our target variable, and based on the data set what we have for 50 odd experiments, with any of the combinations with what we have out of this 1 to 50 combinations, with any combinations that we feed here, we would be able to predict the ultimate bending strength value without conducting any experiment. So based on the experiment, what we have done here, this outcome of this AI and ML here, it will now be giving you the mathematical equations. These mathematical equations will help us in predicting what the ultimate bending strength, that is, I mean, I'll be using the word UBS for this. So in predicting the UBS for the respective material. Now, this design of experiment was done by using Taguchi design of experiment. Or in case if you still do not have any knowledge on Taguchi design of experiment, you can go on with any of the existing DOE models. So Taguchi DOE is not the one which is most often, I mean, which is still most often used, but nonetheless, that's not the one and only technique what we have. Now, with this data set, what we'll now be doing here is, this is the notebook that I've used. That is the Python is the language that I've been used to generate this particular outcome of the project. Now, a small introduction has been given for the project. This project is aiming to predict the mechanical property, especially the ultimate bending strength of a 3D printed polymer material. Okay, this property of the 3D printed polymer is very essential towards dimensional stability and its retention. Okay, in this study, we are now presently focusing on fused deposition modeling technique, that is a 3D printing process. And the testing standards are of ASTM standards. Now, as I told you, the Young's modulus values are related to the polyethylene tetraphthalate glycol, that is PETG, polycarbonate, ABS, and then the PLA material. So these are the 4 materials which are now being used. And then we get to see the respective Young's modulus of the individual material, which are now being tabulated in this table. So this is the table that this is the column that I'm talking about, which is now having the values of 3.5, 2.8, 2.1, and 0.6 respectively. Okay, so the same combination of the 3D printer is now tried out with different materials. So you get to see a set of 10 in each category. Now, how do we start with this Jupyter notebook is, we'll have to import the necessary libraries. These libraries include the pandas. The Seaborn libraries are very essential for us to have a data visualization, which helps in data visualization. And then the matplotlib is the one which helps us in plotting the graphs, extensive graphs, and then the train test splits model. And then we are using a couple of machine learning models. In the present investigation, I have used 4 different machine learning models, that is lasso regression, Ritz regression, and also the Box-Cox transformation. These 3 are been addressed for a single order polynomial equation, which is generated as to predict the ultimate bending strength. And then the final one is the higher order polynomial equation, which helps us in predicting the same ultimate bending strength with a higher accuracy. Now, we mount the drive in Google, and then we load the data set. So we get to see the first 5 rows of the data set. This is just a sample. You get to see once when you execute a command df, that is data frame.head. So now we'll have to do a couple of exploratory data analysis before we get into the stats part of it. This helps us in knowing whether the data is completely balanced or it's an unbalanced data, which means to say like any of the values are missing or any of the values are to be added. So how do we do that is we do the statistical summary. In the statistical summary, we get to know what is the count of it. So as I told you, we have 50 rows in each in the data set, which is now being loaded here. And then the mean of the Young's modulus is 2.24. We'll have to more importantly see this 50th percent value. Okay, so this is the one which plays a vital role in determining the skewness of the data. Nonetheless, the data is completely balanced here. So you don't get to see maximum skewness here. So if you carefully look, the 25th percentile, 50th percentile, and 75th percentile value are pretty much in line with what we get to see between the minimum and the maximum values. So similarly, we have print speed, ultimate bending strength. Okay, now please do remember, we are now using these four as our parameters, that is the factors. One is the layer height of printing, infill density, that is the density at which the product is printed, printing speed, and then the Young's modulus. Okay, so once when we do this, we get to see there are no unwanted data here. So that comes as an outcome of the validation in terms of its statistics. Next, we go to the correlation heat maps. Now, in correlation heat maps, this is the heat map what we get here. Now, I'll just give you a small example of how this correlation heat map works here. Is now you get to see a diagonal value of 1, 1, 1 for the given square matrix. Now, if this diagonal value, either it could be a right diagonal or a left diagonal, that doesn't matter much. But the value of 1, which means to say it is highly correlated, and the value which is slightly lesser than 1 are the one which comes under the second highest correlation. Now, what do you mean by correlation here is, you get to see an example of most often brought products together in Amazon. Okay, like for example, once when you buy a cell phone, automatic recommendation comes in order to buy a screen guard for it, and also a back panel cover, or any other recommendations what you get here. So, and similarly, in case if you do order breakfast in a hotel, obviously there is a high tendency of you ordering a hot beverages like a coffee or tea along with that. So under that case, coffee becomes the high correlation with the breakfast. So similarly, on coming up with the explanation of the Amazon, what we told, the screen guard becomes the highly correlated product with that of the phone. So like this, we mathematically express this correlation in terms of number. Sometimes like you get a positive correlation and also negative correlation. Now, when do you say it as positive correlation and when do you say it as negative correlation? You get positive correlation when both are on the upper axis. Like for example, if you say that more number of product A is brought, similarly, even the product B is also being raised simultaneously. In that case, for example, let's say that a sale is happening in a retail outlet, and then the correlation heat map, I'll just correlate this with an example. Now, if you say that you're buying a product in summer, that is a sweatshirt, your sales of raincoat is gradually down in summer. Okay, so that means to say the sales of the sweatshirt and the sales of the umbrella or the raincoat is negatively correlated. That means to say, as and when the sale of this is high, of the t-shirt is high, that is the sweatshirt is high, simultaneously the sale of the other product, what I told you, that is either it could be the umbrella or the raincoat, that is getting dipped. Okay, so that is an example of negative correlation. Now, this correlation is the one which we'll have to look for in terms of the color identification or in terms of the value. Now, you could say that the ultimate bending strength, what we are now seeing here, it is highly correlated with Young's modulus. So along the top row, what you see here of 0.99, so you get to see with the matching of Young's modulus and then the ultimate bending strength. So this gives a clear idea of the material, irrespective of whatever the printing parameters settings we do. It is the inherent characteristic of a material which plays a vital role in determining the ultimate bending strength of the material. But nonetheless, we are supposed to look into the layer height and also the process parameters to make it even more effective. As like what we get to see in the previous session, you have different sessions. I mean, you have different parameters that are to be looked into once when we optimize the process parameters for a given material. So we get to see 0.99 as the highly correlation with this between Young's modulus and the bending strength. That means to say, higher the value of Young's modulus is, more the bending strength of the given printed product is. Next, highest comes the Young's modulus and the printing speed. So you get to see the value of this. Now, from this value, you could make an inference. That is the key observation, which tends to say like which is under the positive correlation and which is under the negative correlation. With that inference, we come to the next important feature called as feature elimination or feature retention. Now, in feature elimination or feature retention, based on this, we drop out a value which is highly close to zero, not on a negative side, highly close to zero. So the value which is close to zero are your print speed. That is the print speed 0.048. Okay, the correlation matrix itself is telling us to drop this print speed because that is not having an effective contribution in determining the ultimate bending strength of the product. But still, we'll have to do it because in some of the experiments we don't have the freedom to drop any columns. Okay, we have been forced to retain all the columns and then do the predictive analytics for the given material. So under this case, we get to see the feature importance well before we go to the feature engineering. So we have downloaded, we have kept the Young's modulus, layer height, infill density, and then the print speed as the x-axis, and then the target variable is our ultimate bending strength. So we perform random forest regression and then XGBoost. These are the most predominantly used ML models to determine the rank of the parameters that are now being used here. So in this feature importance, as we get to see from the stat itself, it is the Young's modulus of the material which plays a vital role in determining the ultimate bending strength of the given any printed product. So this is one proper justification by using machine learning algorithms. This graph gives us a clear evidence that the process parameter is not that very crucial in determining the ultimate bending strength of the product. But still, the Young's modulus also plays a vital role here. Now, this is the correlation what we get to see between Young's modulus and the ultimate bending strength. So once when we use a material with the higher Young's modulus, we get to see the increased ultimate bending strength for that. Okay, so this is what the relationship between the process parameters and then the ultimate strength is about. And then next, as I told you, we are now getting into the feature engineering state. In feature engineering state, we have the provision to delete or drop any of the columns. Now, before we drop, we'll have to check for its multi-collinearity. Now, if this multi-collinearity is the one which is now how do I tell? It's like two mutual friends having a tie-up together in order to destroy the team. Like for example, let's say that you have cricket. You have playing 11. Out of those 11 players, 2 players are highly multi-collinear, so that they could either win the match or they could either lose the match. Okay. So it's the such combinations between Young's modulus, layer height, and then layer height with infill density, and then infill density with print speed. This combination, any two, whatever we get to see here, is the one which is determined by this variance inflation factor. Now, mathematically, there is an expression which gives us a value of this VIF. But once when I get to see this variance inflation factor, there is a rule which is now been followed very often. It's a thumb rule which has no strong evidences for it, but still in industry, we take a value close to VIF less than or equal to 5. Now, any value or any feature which is having a higher VIF value, that means to say it is not having a big contribution in determining or in predicting the value. So you could see here the Young's modulus is having a VIF value of 6.4. Layer height is having a value of VIF is 5.6. Infill part density is 17.66. Print speed is 16.79. So out of these 4 values, mathematically it is very clear that this infill part density could be removed. In case if we are going for feature elimination, That is, out of these 4, if we are trying to eliminate any 1 or 2, then the machine learning is automatically giving, I mean, the XGBoost and then the random forest model, what we have used here, it is clearly telling that infill part density can be eliminated once when you have the option to eliminate it. But still, this is where the domain knowledge comes into a picture. That is, the core engineering knowledge matters a lot once when you take such a decision, because we clearly know that infill density plays a vital role in determining the strength of the product. So that means to say, practically, I know that infill density has a crucial role in determining the ultimate bending strength. But the ML model is telling that infill density can be eliminated. So here comes an option of deleting or eliminating any one out of these 2. Now, with the common sense what we have in additive manufacturing, that is in 3D printing, we could somehow correlate, come to a conclusion that print speed, it has no significance on the product outcome, that is the ultimate bending strength. Because printing speed, we get to see it's a small value variation what we do here. So that doesn't have much contribution in determining the ultimate bending strength in compared with the infill part density. Therefore, in feature elimination, you could see here the selected features. Now, this is where I'm running the ridge model. In ridge model, we get to see this is a model of ML algorithm wherein you now have the provision to delete or eliminate the feature. Now, in this process, we have the feature that is Young's modulus, layer height, and then the infill density. So the model which is now about to perform this ridge model has automatically deleted the print speed value in the column. Okay, so it is by default, it is we are now selecting it not to choose that column data in order to predict or in order to build the regression model to predict the ultimate bending strength of this. So this becomes our Y variable. So we do the specimen based on the, I mean, we select the specimen based on the train and test model. Here in the model, you have the choice of going with 80-20 or 70-30 as your train and test split model. If the model size is very less, I mean, here we have only 50 rows here. So with this 50 rows, I have taken 80% of the 50 rows as my training model, and then the remaining 20% as my testing model. So this alpha value is one which is a hyperparameter tuning. This we can adjust it with some value, which could start with 0 and then go up to a maximum of 2 or 3. At one point, it reaches the peak and then it drops down. So that point, in Python, you can automatically get the optimum value for this optimum alpha value. So on evaluating the trained data, everything is done now. Now, how do I evaluate the model? The model is evaluated based on the errors. Now, those errors are the mean square error of the training and then the mean square error of the test, followed with R square value. Now, the mean square error is the one which is to be minimum, that is as close to 0. And then R square value is the one which is preferably close to 1. Okay. So here we get to see the train value of 0.9830. This is the R square value. That means to say, out of the 50 datas what we have in the Excel sheet that I showed you, 98.3% of the 50 rows are now being addressed in this model. So that means to say, still 1.7% of the data is still unseen. That means to say, the model was not able to fit those 1.7%. That is 0.17% of the value is still not being trained, because that becomes as an outlier here. Now, once when we correlate that with the test and the trained data, even in the same testing data, we are still in the same ridge model itself. We get to see the R square value, which is slightly dipping. This tends to happen because it is completely dependent on the train test split that we do. Now, on doing so, we now plot the actual versus the predicted. Mathematically, this is, I mean, the upper blue is the one which is predicted, and then the lower blue is the one which is the actual one. This is according to the different models of what we get to see here between the train. This is what you see towards the left is the train, and what you see towards the right is the test data set. And then this is the histogram, which is very important in understanding whether the data is completely skewed either towards right or towards left. Now, we could see a small skewness here towards the left on a negative axis. That means to say the result is slightly dominated on the negative side rather than being it on exactly at the center. Here you could see a slight peak towards the right side in the test data set of the split what we did. So this skewness, this is in an acceptable range because we don't get to see a drastic change in the curve. It's in a slightly uniform peak and then it is dropping down. So this is in an acceptable range. Now, we are now in a stage of building a regression equation under the first model, what I told you, ridge model. Now, this is where we get to see the coefficients and intercept and then the multiplication factors for it. Now, if you want to predict the ultimate bending strength of the given material, of any material of your choice, of any process parameter of your choice, and if you substitute in this equation of 6.46 is the intercept value, and these are the coefficients of Young's modulus, coefficients of layer height that is to be multiplied, and then the coefficient of infill part density. Once when I get it, this becomes my actual versus the predicted model, which I get to see between, this is my row number 28, row number 11, row number, that is experiment number 28, 11, 10, 41, 2, 27. This is randomly chosen. So these are the 20% test data, and then the actual predicted value, of the row number 28 is 45. So we get a predicted value of 43.27. Row number 11 is, experiment number 11 is having an actual value of 55 megapascals. But according to the predicted model, you get to see a value of 54.72. And this is the way how we get to see between the difference between the actual and the predicted model. So if my mathematical equation is 100% correct, that means to say, I'll go back to the model evaluation. If I get this mean square error as 0, and then R square value as 1, if I do get it under the testing condition, under the test data split, that is, let's say that I have not got this 4.405, I have got it as 0. And R square value, instead of getting 0.975, let us take that I have got 1. Under that case, the difference between the actual and predicted would have been 0. If the actual is 45, even the predicted would have been 45. Now, this changes does happen because in 3D printer, we don't control the atmospheric temperature. That means to say, while printing, we leave the printing chamber open, or maybe it's not completely air packed. So as a result, there are a couple of noises which gets added on into the noise contribution while predicting. That's where we get to see these differences. All right. So in the first stage of ridge model, we have eliminated 1 out of the 4 features. Now performing the next machine learning algorithm, because I'm not sure whether this is the best. I'm in search for the best model. Now I want you to look at this equation. Now this is an equation which is of a single order polynomial. That means to say nowhere you get to see a square component or square root or cube root. So this is called as single order polynomial equation. With that, we get to see this difference. And then in the performance using lasso, lasso is one more cross validation method. In this cross validation, we are not supposed to delete any of the features. Okay, this is the rule of lasso. Okay, in ridge, we have the provision to delete, but whereas that is feature elimination is possible in ridge, but in lasso, we are not supposed to delete any of the parameters. So henceforth, all the 4 we get to see at the initial stages are retained as X itself. And then we are now determining the ultimate bending strength. Now, thus we get to see the lasso. This is a code which automatically takes care of the optimal lambda value, optimal alpha value. So this alpha value is now chosen to be I mean, the machine learning is recommending the alpha value of 0.2531. So this value is now being chosen automatically. And then in the model, I get to see an error of a training data set of 4.798 and R square value of 0.9842, and then mean square error of 4.56 under the testing, and then R square of 0.9745. Now, we'll have to perform the same data visualization by doing the actual versus the predicted model. Now, here you get to see the R square value of 0.98452. Now, what does this mean to say here is the red line, what we see here, this is the ideal fit line. This has taken care of 98.42% of the dots, of the blue dots. Okay, if these blue dots were completely far away from the red line, that is the ideal fit line, then our R square value would have been very less. Okay, so the ideal fit line is the one which is passing through all the predicted. Okay, so that's what I mean. This is quite a challenging task to fine tune this in order to get a R square value of close to 1. But in case if we do get close to 1 or 1, that becomes a pure example of overfitting. I'll tell you what overfitting is in the later stages, because once when we do the overfitting, the model completely becomes like a parrot. Like whatever we tell, it'll just be mimicking and then giving back the same without learning anything from the data set of its own, by its own. Okay, now we are in the lasso condition. Now in this lasso condition, this is the histogram what we get to see here. There also in the ridge model, you get to see a left skewed. Here in the lasso also, you get to see the left skewness here. Similarly, on the test data set, we get to see the right skewness. Now, this is the regression equation, which we get according to this. Now, what is y? Y is basically this is the equation. Y is basically our ultimate bending strength. But if you get to see here, automatically 2 features are eliminated. That means to say, we don't get to see any components. We get to see one coefficient. This is the intercept value, and this is the coefficient of Young's modulus, and this is the coefficient of infill density. But we don't get to see the coefficient for layer height and then the printing speed. So that means to say that coefficient is 0. Anything that is multiplied with 0 is not having any significant input mathematically. Therefore, here a clear-cut information has now been written, including only the non-zero coefficients. So henceforth, you don't get to see here. Get to see the other 2 parameters, that is the layer height and also the print speed, according to the machine learning algorithm what we are doing here. Now, if I get to see here in this model, this is my actual value, this is my predicted value. I mean, at the end, I have the consolidated result of all the 4 machine learning models what we'll have. That's where we now come to a conclusion that which model works out better for the given data set. Now, we get to see the actual and the predicted values of the ultimate bending strength for the same respective rows, which has now been taken as the test data. Okay, so this is where we complete our second machine learning model. One was the ridge, second is the lasso. Now, what we are doing here is we are trying out with a higher degree polynomial equation. So we are trying to increase the efficiency of the machine learning model or the equation, apparently the equation, to basically come closer to the actual value. That is the prediction value minus the actual value should be close to 0. That's what our primary objective here is. Now, once when I add polynomial equation, now here I'm giving the extension up to a degree 2. I'll be getting a higher order polynomial equations. Now, I'm using a linear regression model here. In this linear regression model, we have the model evaluation, which is done by using the R square value and then the mean square error. Now, if you look at the higher order equations, now you get to see a rapid jump from 98.3 to 99.85% in both test and train. So that means to say, once when I mathematically go with the higher order polynomial equations, it has now been reduced from 5 point change to 0.4, 0.5. You can round it up to 0.5. Okay, this is where the error in the machine learning model is now reduced by just making the RHS of the equation to have a higher order polynomial equation. Now, how do we generate that equation? Okay, here you get to see the R square value is 99.85, which is almost touching all the blue dots that you see here and also all the green dots that you see here. And then the residue, this is where you get to see the importance of the histogram in training data set. As we get to see here, the training is addressing almost close to 100% of the data. If that being the case, then this is the ideal inverted dumbbell shape, which we ML engineers look as the perfect fit model. This is our dream result, actually. Okay, you should be getting a result of this. So once when you get a result of this, this is where we get to see this is the best ML model. So mathematically also we have proven, and graphically also we are proving that the model is best for the given expression. But nonetheless, this is not just the one. I mean, this is not where we could end here. We are supposed to generate the intercept value of that and also the coefficients of that. Now, if you look at the final regression equation, this is the final regression equation by using higher order polynomial equation. This is the intercept value of 0.369, the coefficient of 25.27 for Young's modulus, coefficient of 7.25 for layer height, coefficient of minus 0.07 for infill part density, coefficient of 0.31 for print speed, and then you could see here you get a value of Young's modulus square. This is where I now told it's a order of 2 equation with a higher order polynomial, and then the higher order polynomial is of a second order. So how do I substitute this? Now, for example, you can easily do it in your Excel or the same conventional calculator. Now, how do I predict the values? Take your calculator, substitute minus 3.69 plus 2.27 into any of the Young's modulus value of your choice, plus 7.25 into any of the layer height of your choice while you print, that you are about to print, and then minus 0.07 into infill density percentage, that is 70, 80, 90% or 100%, plus 0.31 into print speed based on the data what is now being printed. So all these substitutions you do, for example, let's say that you are having a Young's modulus of 0.6. In this equation, you are taking it as 0.6 square. With a simple substitution in this equation, by using a normal scientific calculator or probably using the Excel sheet, you would now be getting the actual and the predicted value. Now, if you could see here, the actual value is 45, but the predicted is close to 45, 48.87. Now, if this doesn't say that it is completely on a upper hand, that is, you will be getting a value of the predicted value less than what you're supposed to go. No, sometimes you will be getting still on a higher side than what you're supposed to get. Here you get to see 55.95, which is on slightly higher than 55. So this trend, I mean, this is the normal trend wherein we don't have any control on the predicted data, whether it is on a complete positive or a negative side. Okay, that is where we now end the third ML model. And then the final model, what we get to see here is, we'll be using the Box-Cox transformation. This is also very essential transformation. Like in transformation techniques, we have XGBoost, AdaBoost, Box-Cox transformation, and a couple of more techniques what we are now implementing. Now in Box-Cox, because most of my papers until now where we predicted the target variable were using Box-Cox transformation. But now based on my inferences, I still tried out with Box-Cox transformation. We retained all the 4 features here, and then the bending strength as our target variable. This was the model, and then I could not go less than what I got for a second order polynomial, even which was best according to the previous case studies, that is Box-Cox transformation. Even this is now giving me a mean square error of 2.27. But whereas higher order polynomial equation gave me an equation less than 0.5. So that means to say even this model is not best fit for the given set of data. So as a result, we now get to see the equation of this, and also the same testing data what we get to see here is also done. And then the skewness, it is completely on a center, slightly towards left. Here also slightly towards left. The skewness is on towards the left. And then we use the regression model as lasso what we use, because we took all the 4 features here without eliminating. This is where we now get to see the actual and the predicted values. Okay. Now, altogether we have undergone, or we underwent 4 different models. One is lasso, ridge, Box-Cox transformation, and the higher order polynomial equations. Now, how do I get to see as a consolidated result is here. Now, for a predicted model, this is our prediction. This is our actual value. The first column, what you see here is the actual value of. Now, the ridge model, by using ridge model, I was predicting, instead of getting 45, the model showed me a value of 43.270. The lasso model 43.10, Box-Cox transformation 44.49, but wherein the higher order polynomial equation gave me a prediction which is close to 45. Now, if you look into that, the extreme last column what we have here, this is very much in line with the target column. So with this 4 models we have tried, we could tell, or we could conclude that a polynomial equation which has been built by using a regular linear regression model of a higher order polynomial gives me a best. Now, if I could go with a third order polynomial equation, now why did I stop with second order polynomial? Why didn't I go for a third order polynomial? Now, in case if I go with a third order polynomial or even higher order polynomial, the mathematical equation becomes more and more complicated. That is, you'll be getting in terms of x cube, y cube, z cube. That is basically the factors multiplied with the cube values. So the computational time will be maximum. So in order to reduce the computational time, and also we don't have the control over the noises that we get while printing, that is also to be considered. And then we limit ourselves to the second order polynomial equation. Now, if you get to see here, in terms of errors, on taking the average, the ridge model exhibited an average of average error of 5.10 in the prediction according to ridge and the actual. In the prediction according to lasso and the actual, it exhibited me an error of 4.83%, and Box-Cox transformation had a deviation of 3.05%, but whereas higher order polynomial had a very less deviation in between the predicted and the actual model. Okay, so with this, what we could say here is building a machine learning model with a higher order polynomial equation is much preferable, and the equation what we have gotten here is the one which is best suited, that is the higher order polynomial equation. So this is the equation, not this. Yeah, this is the equation which could be strongly recommended for any of the machine learning, any of the 3D printer researchers or the manufacturer to predict the ultimate bending strength. Now, if I make this equation visible to anybody, they could directly dump their process parameters in this equation, and then they could be predicting what the ultimate bending strength could be without conducting any experiment. For any material of their choice, provided they get to know the Young's modulus value of it. But however, in this study, there is a limit for it. In this study, as I told you in the beginning itself, we are trying out with only 4 different materials, and those materials are PETG, polycarbonate, ABS, and polyamide, which is having a starting value of 0.6 GPa to a upper limit of 3.5. That means to say, this machine learning model holds good if you have the Young's modulus of the new material that you're now printing is lying its Young's modulus between 0.6 and 3.5. Now, what in case if I choose a completely different polymer material which is having a Young's modulus of 4 or 4.5 or 5? Under that case, this mathematical equation, what this ML model has generated, will not be valid. It will not be valid because that equation is generated by keeping the lower limit as 0.6 and then the upper limit as 3.5. Okay, so once when I have to do that, then yet again I'll have to build the data set here. I'll have to add a new column here for the respective Young's modulus. Once when I increase the number of experiments here, and that's where the mathematical equation gets changed, and we are not sure whether it's the same old sequence that gets followed here. Yet again, you'll have to run different combinations of the experiments in order to tell which is best. Okay, it is not always necessary for us to have the higher accuracy with the equation having higher polynomial orders. Some obnoxious things also could contribute here in such a way that any one out of these 4 could stand as the best. So this approach is very advisable and suitable in order to build a mathematical expression through the machine learning. Now, the decision of what we get here and what to choose is completely dependent on the subject matter experts. Okay, however, this is just the prediction. Once when we do it practically, the results might vary. I'm not sure. I'm not very 100% confident enough in telling whether you'll be getting the same as what the machine learning model is. It's just a prediction, which is close to 99.85% similar to the actual one. Because while printing, as we saw in the previous video, there are many parameters which play a vital role in having a negative impact on the product strength. It could be the contamination in the spool. It could be the non-uniform deposition of the material. It could be a layer jump, which happens during the machine, or a slightly offset while printing, especially once when you print a slightly inclined component. This test conditions holds good only in case if it's a flat component, how we do in the ASTM testings, like a dog bone shaped specimen, and then a rectangular specimen, and then a cylindrical specimen for a pin on disc test. So, however, this is just for the ASTM. This is as per the ASTM test conditions what we have gathered the results. But nonetheless, once when we go for the product, yes, product profile matters a lot. And then this supporting structures, the way how the supporting structures are laid by the machine, that also matters a lot. And then the orientation at which we now start printing, that is also a matter a lot. Now, this is what the overall point I wanted to tell in the case study. So with this, I keep the platform open for the questions.
Thank you, sir. Participants can enable your video and directly you can interact with Dr. Nagendra, sir. Participants, kindly ask the queries.
Hello, sir. Sir, in the chat
Yes,
box, there is one question, sir. Nagendra, sir.
Yes, sir. I'm just looking at it, sir.
Yes, sir. Yes, sir.
Sir, Dr. Rajkumar, sir has commented. He has sent a message that, okay, first and foremost, he has thanks a lot, sir. Can we able to do design the experiment and do complete optimization using Python? Like, yes, sir. You can do this. You can do this RSM. You can do this. The mixed variable analysis also. All these things can be done. it can be done using Python. That is the answer for your first question. Nowadays, research articles with only optimizations are not easy to publish good journals. So what can be added in order to get published? Sir, along with this, what we get to see here is the optimization. Yes, if you go with just one single design as the best, that's where the paper gets rejected. If you have a validated model, which gives you difference of answers and whichever is recommending the best. So you need to have at least right now at least 4 to 5 different models to compare and then tell which is best. So if you have 4 to 5 different models and then if you recommend which is best for the given data set, so obviously in an easy go your paper gets accepted. That is one thing. And obviously we cannot tell, you'll have to use all different models of ML to validate your results and then recommend which is best out of all the ML models that you have tried. And to adding on with what sir has said, that is Dr. Rajkumar sir, if you conclude your result with experimental ASTM standard test results for your prediction and what the actual test is, so that gives you a better strong hold in telling like what you have got and what you have predicted. Okay, so that makes a better meaningful sense in order to complete your project or probably the paper. I hope I have answered to both of your questions here. And now design of experiments is not, I mean, we used to follow Taguchi design of experiments. Now that is nowhere needed now. That is nowhere needed. You can go with any combinations what you get here. And you get the data sets from Harvard universities. It's not necessary for you to test your own, get your own results. You get the results which are already been published by some other scholar. Okay, so you can write a mail to them in order to use their data. So they'll definitely acknowledge it because they are the primary data source owner. Before we publish, we'll have to take their permission. And because the data set what I'm using here, it's not my data set. It's a research scholar who is in Germany. So I have taken his permission to perform this investigation. And there is a mutual agreement between us. So once when I do publish a paper on this, so his credentials are also to be addressed. So that mutual collaboration you can have with any of the dataset owner. Okay, with that you could do a significant contribution, and these papers are, I mean, it gets very easily accepted. Okay, you get to see very less competitive papers under this domain. So it's better we make use of it at the earliest. Okay, next, Dr. Vidyadhar sir has posted a question. How will additive manufacturing integrate with other technologies such as artificial intelligence and Internet of Things? Sir, this Internet of Things is the one which plays a vital role in data capturing. That is, we call it as data mining. These data mining are done by using the IoT tools. Like, for example, you have Blink software, which automatically records the reading what your IoT devices, that is your sensor, takes in. It could either be a pressure value or a temperature value of anything as such. So those readings are the one which gets recorded at a different time. What you said, for example, at a baud rate of 2 seconds or 5 seconds, every 2 seconds or every 5 seconds, you get to see the result. For example, let's say that you're running your IC engine with a half-filled engine oil, and then you get to see a temperature of it by using the IoT tool. There you get to see a data of the IC engine being run with a half-filled oil, and similarly top it up with another few more ml of oil, like 3/4 filled or completely filled engine oil into the engine, and then you get to see the outcome in terms of the temperature measured with that engine. So that's how you can correlate your IoT with the regular machining. But in terms of additive manufacturing, IoT, we don't get to see an integration of IoT because most of the devices, sophisticated devices, are an integral part of the machine. So any further advancements or integration of IoT in AM is challenging because we don't get to see the software customization. It's a Cura software. which is readily available. So we don't have the provision to edit it, I mean, customize it. So as a result, implementation of IoT, it is only in data mining, but not in data augmenting. Now, T. Shankar, Professor T. Shankar has asked, what are the key parameters that influence the quality of the parts in SLM? Sir, in SLM, it's completely dependent on the material that we use and the conditions that we are now looking into, sir. So probably a proper validation, you could justify it by looking at the papers which are already been published. So that makes more sense. And rather we predicting our own assumptions. So it's better we look into the papers which clearly gives an overview of which factor dominates a lot in determining the quality of the product in SLM. Yes, sir. Thank you, sir. Thank you, sir.
Any other questions from the participants?
So anyone can give this online feedback with enabling video about this session. Is there Vijay Rai, sir? Arun Kumar, sir, can you give this feedback about this session? Yes, sir. Actually, this is a wonderful session. Sir, give us more information about this. The Python, how it is related to this, the various domains. Actually, sir is in purely mechanical background, and then that based on their interest, own interest, he did this project in AML, and then PG also completed. Personally, I know how he is dedicated, how he is worked in this different field. He having the more knowledge as well as more experience. Then now, sir, sir delivered the wonderful informations. I hope everyone received this a lot of information. Definitely, it will be more useful to their project. Definitely, maybe collaborate with mechanical background with any other department like a EC, CSE, nowadays the AML, like that. So I hope that the session will be more useful to everyone. Thank you so much, sir, for accepting our invitation, as well as you delivered such a wonderful information about the recent trends. Thank you, sir.
Thank you, sir. Thank you, sir. Welcome. So this was the last minute change. What I did after looking at Dr. Srinath's presentation.
Yes, actually.
Because I don't want it to give the same. I don't want it to give the same thing. I wanted it to take it over from where he left.
Yes, sir. This is another part actually. It's a combination of both, but it's a very interesting. So everyone got it.
Thank you, sir. Thank you, sir.
Thank you, sir. Eman, sir.
Yeah. Thank you very much, sir. Nagendra, sir, the session was very informative. So along with the prediction software also, along with the additive manufacturing, 3D printing, so the session was very useful, sir. So most of the researchers, those are pursuing PhD in this particular area, definitely they have taken this advantage of this particular session. I thank you very much, sir. And on behalf of New Horizon Management, Principal, Dean, Director, HOD, and faculties, I thank the session speaker, Dr. Nagendra Jairam, sir. So for his for taking his particular time on transferring the knowledge on the topic 3D printing in the modern industry, as well as about the prediction software also. It's a great learning for all of us. Thank you very much, sir. And I also thank ACT Atal for giving us opportunity for conducting this program. Thank you all the participants for joining the session. And I'm going to post the feedback link and the quiz link in this platform. I request all of you to kindly fill this link and it will be enabled up to 20 minutes. So thank you one and all. Thank you, sir. Thank you very much, sir.
Thank you, Hemant sir. Thank you.
Thank
All
you,
the
sir.
best. All the best
Thank
for
you,
the
sir.
remaining days.
Thank you, sir. All the best, sir.
Thank
Thank you, sir.
Thank you, Nagendra.
Thank you, sir.
Yes, sir.
Thank you, sir.